Good morning, everyone. We are going to hear from Carl Meyer about getting started with testing. Carl is a core committer on Django. He works with virtual env and pip, so please give him a warm welcome.
Thank you. So a little bit about the plan for the next 25 minutes. I'm going to start off talking a bit about why you might want to write tests, how you might write tests, how to run your tests, what kind of tests to write, and a little bit about how to integrate testing into your development workflow. Quick story about me and Python and testing. I've been writing Python since 2002, professionally since 2007, writing a lot of tests since 2009. I enjoy writing tests so much that this slide deck has tests to test the code samples in it. I mostly do web development in Python. This talk is intended to be general beyond just web development, but that's my background. In terms of open source software, I've done some work on pip and virtual env and on Django. So if you use those projects, you may have used some of my code. Let's make something. The plan for today is to make a GitHub recommendation engine. It's something that will go out to GitHub and look at the repos that you're watching, find people who are watching similar repos to you, and inform you about repos that people similar to you are watching that you may also be interested in. It's actually been done already, but that's not a problem. Here's the function we'll start with. It's a similarity function. It gives us a similarity score between two GitHub users. We pass in two iterables of repository names that two different users are watching, and it'll give us a similarity score between those users. The similarity score that we use is the Jakarta index, which is the intersection of the sets divided by the union. Because this is software development, we're going to start out with an implementation that is slow and buggy. So that's what we have here. We iterate over the two iterables nested to build up a count of the intersection between them, and then we calculate the union and return the one divided by the other. So we want to make sure it works. We fire up the Python shell, and we try it out. We feed it some sample data, which we manually calculate what the correct answer should be. In the first case, the intersection between those two is B, and the union is ABCD, so that's 1 over 4. It should be 0.25, and in fact, that's the answer we get. We try another couple tests, and it seems to work correctly. But there is a bug. Our buggy implementation doesn't know how to handle duplicates correctly. So in this case, the union ought to be AB, but instead it's calculated as AAB, so we get the wrong value. Fortunately, Python has a very nice built-in set implementation, so we can make our buggy implementation less buggy by using that. And that also has the side effect of taking care of duplicates correctly. And in fact, that does fix our bug. Now, even if we pass in lists with duplicates, we get the answer out that we expect, 1/2. But we rewrote every line in the function, so we better fire up the shell again and run all of our previous tests again to make sure we didn't break anything. And in fact, we go through and verify each one manually, and they all still have the same answer, so congratulations. We didn't break anything with our change to the function. Now this gets old, and it gets worse the more complex or the bigger the system gets. I was asking on Twitter about why people test, and I heard one story from Kumar McMillan about how he used to work on a 14-page survey app with manual testing, and anytime he would make a change to the 14th page of the survey, in order to see that change, he would have to click through and fill out 13 other pages of the survey, and then load the 14th page, and then verify his change. So this is repetitive and boring, and we know what happens with repetitive and boring tasks. We skip them because we don't like to be bored, and then we ship broken code because we haven't tested it. Also, this kind of manual testing is not easily reproducible. If you're running manual tests in your shell or in your browser or whatever, and you find a bug, you have to then copy-paste your shell session or try to describe what you did in the browser in English prose and send that off to your other developers in the project and try to see if they can reproduce the same problem that you found. Also, it's error-prone. Did you look carefully and verify all 3 of the examples I had up and make sure that the answer was correct? Did I do it correctly the second time I did it, or the third time, or the 4th time? We make mistakes when we do this manually. Fortunately, we are software developers, and therefore we know what to do with boring, repetitive tasks. We automate them. So let's try that. We're not using any special tools here, just regular Python. We create a second file, test.getrex.py. We import our function that we want to test, and we write a couple asserts. We call the function with some input, we assert the output, and we fix several of the problems that we had before. Now we can run this automatically anytime we want. It's going to run the same tests every time. If we make a mistake the first time we manually calculate and write this test, we'll eventually catch that mistake, correct it, and then we have the benefit of a fixed test for good. We don't have to rewrite it every time. And if we discover a bug, we can record it as a test in this file, send it off to another developer, and feel fairly confident that they'll be able to run this test file and see the same bug that we saw and then help us fix it. So here, we found a bug. Let's add a test for it. Another bug in our implementation of similarity is that it doesn't handle empty sets correctly. If both sets are empty, the union ends up being empty, and therefore we try to divide by 0. Now this reveals a little bit of a problem with our simple testing setup here, which is because we inserted this test as the first one in the file and it failed, Python just gives up there because of the exception, the 0 division error, and none of the other tests get run. This is still okay if our main goal is just to see if anything broke. We see that in fact something is broken, but it doesn't give us a complete picture of the state of the software. We don't know that those other 2 tests still pass, and that some things work and this one particular case is broken. All that we know is that something is broken and we don't have the rest of the information. It'd be nicer if we could see the results of all the tests at once. So we can do that with a little Python. We move our assertions inside functions, and then we write a little boilerplate at the bottom of the file. So if this file is run as a script, it loops through each test function and runs each one within a try block. And if there's an exception, it prints out that there was a failure with that test. And if there was no exception, exception could include an assertion error, of course. If there was no exception, it prints out that it passed. And so we run that and see the output below. And in fact, it works. We see the result of each test. 1 failed and 2 passed. So that's an improvement. Fortunately, there are tools that other people have built, so we don't have to write all that boilerplate ourselves in every file of tests that we write. One of these test runners is PyTest. That's the one I'll be showing today. There are others. And with PyTest, we can just eliminate all that boilerplate we just wrote and just write our tests themselves. So here's what we see if we run py.test without making any other changes to that file. Because we named the test file beginning with the word test, and we named the functions within it beginning with the word test, PyTest knows how to go out and automatically discover those tests and run them, each one isolated, so all 3 of them run. We see an F and 2 dots, meaning that 1 test failed, 2 tests passed. And then on the test that failed, we get some additional debugging output showing us where in the code the problem occurred. So that's very helpful, much better than our homemade version. PyTest will also let you run just 1 test file or just 1 test, things like that. But in this case, it's just discovering everything within the directory. So now we can fix the bug. We just add in 2 lines to check if the union is empty. And in our case, we'll consider 2 empty sets to have a similarity of 0. And now all 3 tests pass. We can ship this code, and we can have some confidence that if we change its implementation in the future, the existing tests we've created, if they still pass, the function still works. And if we break anything, running these tests should catch that. We'll do a brief digression here because some of you might be wondering what else is there besides PyTest. I don't want to take much time on this because getting caught in picking a test runner or any other tool is a trap. You'll do better to pick one, run with it, write some tests, and then come back to that choice in a year once you've got some experience working with one of them. But just to run through what they are, PyTest is one, Nose is another popular test runner. Both of these are similar and can run the kind of tests we've been looking at here, simple function tests with asserts. Unit test is a test framework in the standard library of Python. It's similar to the XUnit standard test frameworks in many languages. The tests that you write require a little more boilerplate. There's others, twisted.trial, zope.testrunner, and probably others that I'm missing. Just to show you what a unit test might look like, because you'll probably see a lot of them, you have to inherit from the test case class, and then you have to write your tests as methods, and you use helper methods on the test case class to make assertions, like self.assert equals in this case, self.assert equal. So, why write tests? First reason we just saw, probably the most popular reason, tests tell you when your code is broken. As Jacob Kaplan-Moss said on Twitter when I asked about why people write tests, it's more fun to write tests on weekdays than to fix bugs on weekends. Another reason to write tests is that they're a form of documentation. They aren't sufficient documentation, but they help later developers understand the intent of your code. If a later developer can come along, read your tests, if your tests are well written, read your code, that helps them understand the intent of the code you wrote and what it's supposed to do. A third reason to write tests is that writing tests can help improve the design of your code as you're writing it, if you listen to what the tests are telling you. We don't have a lot of time to dig into this. We could do whole talks on this subject. We'll just look at one quick example of how that can happen. I'll tell you a little secret. The nice, simple version of similarity that you just saw is not actually the first version I wrote when I was working on developing this GitHub recommendation engine. The first version looked more like this. There was a GitHub user class, and it had a getWatched repos method that went out to GitHub's API and fetched the repos that that user was watching. And the similarity function actually took 2 GitHub user instances and fetched each of their repos and then did the similarity calculations. It worked fine. And if we try to write tests for that similarity function, we end up with something like this. We don't want our tests to actually go out and ping GitHub every time we run them. That's not polite to GitHub, and it makes our tests fragile if the network is down or the data on GitHub is changed. Our tests may fail for spurious reasons, even though our code is not broken. So to avoid that, we write a fake GitHub user class that we just pass it some watched repos, and its getWatched repos method just simply returns that back to us and doesn't go out and talk to the network. Now, using fake objects like this is a perfectly good testing technique for when a piece of code that you're testing has a complex collaborator, and you don't want your test to exercise that collaborator. So there's nothing wrong with doing this. But in this case, we notice that if we are writing a bunch of tests for similarity, the purpose of all of them is to test various cases in our Jakarta index calculation. But now all of these tests are kind of cluttered up with this boilerplate of the fake GitHub user that we have to create for each test. And the tests are less clear than our earlier tests. And so that's a hint to us that if we're repeatedly having to do this in all our tests, maybe our similarity function knows too much about the world. The idea here is that testable code is maintainable code. Code maintenance is about managing changes to your code in the long run. And the less a given piece of code, a function, a method, or a class, knows about the world outside of it, the more robust it is against changes in the world. It's called the principle of least knowledge. And similarly, the less a function knows about the world outside of it, the less of the world you have to set up in order to test that function. So we just saw that. This initial version of the similarity function knew more than it needed to about the world outside to do its job. It knew about the GitHub user class, it knew about the getWatched repos method, and because it knew all of that, it was harder for us to write our tests, and it would be more difficult to maintain in the future. So the tests gave us a clue that we could focus the simplicity function more clearly on its purpose, eliminate the distractions, and write more maintainable code. That leads into a discussion of different types of tests. In very simple terms, unit tests are the kind of tests we've been looking at so far. They test one unit of code, a function or a method, generally in isolation from other pieces of code that it calls or uses or depends on. Not necessarily 100%. If a piece of code has collaborators that are simple and that are very close to it in the code structure, we may say, okay, that's fine, we'll just let it call out and use the real version of that collaborator. But we generally try to isolate it from complexities and limit the amount of code that our test is exercising So these tests tend to be small and fast. They don't exercise much code, and they're focused. So that means that failures are informative. When a unit test fails, because it's not exercising very much of our code, we should have a fairly good idea exactly where to go look to fix that failure. So they help us debug. Unit tests do tend to require more refactoring. They are tied to the structure of how you've organized your code because they're testing units of your code. And so when you refactor your code, you often have to refactor your unit tests as well. A second type of test, generally speaking, are integration tests, which are higher level tests that test that the components of your system talk to each other correctly. These are slower because they exercise more code. If you write all of your tests this way, your test suite will run slower and it will be harder to run often as you're developing. These tests can be at various layers, all the way from simply testing that 2 or 3 components interact correctly, all the way up to black box tests that go end to end through your system as a user would, and check that the entire system is operating as it's supposed to. These large-scale black box end-to-end tests are also called sometimes system tests or acceptance tests or functional tests. All of this terminology is very confused. If you ask 5 experienced testers what these terms mean, you'll probably get about 10 answers. So don't worry too much about the terminology, but that's generally the idea. So one thing that's hard about getting into testing is figuring out how to integrate it into an established development workflow that doesn't include testing already. One question that often comes up is, should I write my tests first or should I write my tests after I've written the code that they're testing? Sometimes there's a little too much religion wrapped up in this question. The real answer is that your tests will help you either way. Personally, I find writing tests first is more fun. The reason is, for me, that you get to first think about what the code should do, write a test that expresses that, and then get the satisfaction of writing the code to make that test pass. When I write my test second, the psychology is more, okay, I've got my code working, I could be done, but now I have this extra chore that I have to do afterwards. So we'll talk about some workflows. Here's one workflow, a test-first workflow for adding a feature to your software. You first write a system test, an end-to-end test, describing the working feature from a user's perspective. And there's a lot of tools we could talk about for doing this. Some of them let you actually write this test in English phrases. You don't have to do that. There's pros and cons. But in any case, you're trying to describe what the feature looks like from a user's perspective when it's working correctly. And then you start implementation on the feature from the outside in. So starting from the highest level of your code, wherever, like for instance, in a web app, it might be the viewer controller function where a request comes in and it sends back a response, the code that the user interacts with most directly. And you can program by wish. You can implement this highest level of your code, and as you get to some complex detail, you say, I really wish I had a function that I could call with this input, and it would give me back an output in this format. And when you run into that, you can just write your code as if you had that function, even though you don't have it yet. And then you stub it. You create a fake version of it that doesn't actually do anything. It just returns some fake data in the right format that makes your high-level test pass. And then once you've done that, for each stubbed function, you go back, you write some unit tests describing how that function actually ought to work to do its job, and then you complete its implementation properly to make those unit tests pass. Here's a simple example of what that might look like. If somebody was using our GitHub recommendation engine as a library in Python, the highest level function they would call the exposed API might be a function called recommend repos for that takes a username. And as we're starting to write that, the first thing we think is, I really need a function that can get me all of the repos this username is watching on GitHub. So I just write that line of code as if I had that function, create a fake version of it that just returns some data. Doesn't actually do anything, it just returns sample data in the right format. And then I can go ahead and finish out my recommend repos for function, and I can even make my test pass, and then I can come back and complete the implementation of each stub with unit tests. Another workflow is something called a spike. Sometimes if you're starting on a new problem, a type of code, a type of problem you haven't addressed before, you maybe don't have a very clear sense of how the pieces fit together or what the shape of the code is going to be. And it can be hard to write tests when you don't know yet what the shape of the code is that you need to write. And in that case, the idea with a spike is that you dive deep into the problem, just writing a bunch of code, just to learn about what the problem, how the problem looks and what you might need to do to solve it. And you don't worry about writing tests. And now the strict test-driven development says that after you've done that and you have this new understanding of the problem, you delete all that code and you start over writing tests first. I think that's worth trying a few times. It can be informative to see how your second version that you write test first differs from the first version that you wrote when you were spiking. But I don't really make that a general practice. I usually keep the spike code and refactor it as I write tests. A simpler workflow is the workflow for bug fixing. You find a bug. The first thing that you do is you write a test that fails because of that bug. We call this a regression test because it sticks around in your test suite and it ensures that you aren't going to recreate that bug later without being aware of it. Until you've written a test that fails because of a bug, you haven't really identified what the bug is. This is the definition of the bug. Once you have that, you focus that test as closely as you can on the code that is buggy. This often means you write a unit test. And then you fix the code so the test passes, and you ship it. So that's pretty simple. Last workflow we'll talk about is if you have an extensive code base that's already working, already in production maybe, and it doesn't have tests, it probably isn't structured to make testing it easy, particularly at the unit testing level. So what you can do here is you start with system tests that verify the features you care most about, that they work end to end the way you expect them to. And even if that's all you do, you've still won. You now have tests that you can run that verify that the things in this code base you care most about haven't broken whenever you change the code base. And that's a big win. It allows you to make changes to your code base with less fear. If you do choose to go on, the other thing these system tests give you is some confidence that you aren't breaking things when you refactor and improve the organization of the code internally to allow you to also write unit tests for it. Code coverage measurement can be particularly useful in this workflow to give yourself some idea of how well you're doing at achieving tests that cover everything that your code base does. Code coverage is a metric that tells us, in the execution of my tests, how many of my lines of code were executed. Here's how we can do it. Fortunately, Ned Batchelder has written the coverage.py module, which makes this very easy. We can pip install coverage, and then we can coverage run and give it any Python script, and it will run that Python script and measure which lines of code were executed. In this case, we tell it to run py.test. We also tell it to measure branch coverage, which means that in addition to just measuring which lines of code were executed, we also measure for every conditional statement whether both paths were taken. And then the third command there generates a nice HTML report looking something like this. This would be a sample coverage report for our similarity function if we had added the case to handle two empty sets but had not yet written a test for that. We get a red line showing us that the return 0 line is never executed. The yellow highlight shows us that in that conditional statement, only one of the possible paths out of that conditional was taken. So looking at this, we get a very quick visual sense of what test we need to write. Oh, we're missing a test to test the case where the union is empty, where the two sets are empty. Now we can go write that test, and then this whole report will be clean. There's a lot of other tools that we are running out of time to talk about, but that will be useful to you in testing. If you're writing a Python library, you often want to support 3 or 4 different Python versions with that library, and you may have a dependency. If you're writing a library that works with Django, you may want to test it with 3 different versions of Django. You very quickly get to a matrix of 8 or 9 possible combinations that ideally you'd like to test your library on, and that's very painful. Even if you have an automated test suite, now you're talking about manually running it 8 or 9 times in all these different virtual envs or whatever. And so Tox takes care of all that for you. It lets you set up the matrix of dependencies and Python versions and just run one command, and it will run all of these It will run all of your tests under all of those configurations and report what passed and what failed. So that's very useful. Mock is a library. We saw earlier the fake GitHub user class that we created in one test. Mock is a library to make that sort of pattern easier. Didn't have time to get into it, but you can look into it. It's actually included in Python 3.3. WebTest is a useful library for testing web apps at the Python level. Send a request, get a response back. It gives you lots of utilities for making assertions about the content of that response. At an even higher level for web apps, Selenium will let you automate a browser and actually simulate clicks and all of that so that you can test a web app, including the HTML, the CSS, the JavaScript, etc. So, coding with tests is fun and satisfying. Nothing like the pleasure of seeing all of those dots when your tests are all passing. It reduces repetitive, boring manual testing, replaces fear with confidence, results in better code. It is real engineering effort. Test code needs to be maintained and refactored and cared for just like any other code, and it is hard work, but it's worth the effort. Thank you.
Am I on? There we go. We have about 4 minutes for questions. If there's anybody who would like to ask a question, please line up behind that microphone over there and ask your question.
Thanks a lot, Carl. It was a great talk. I'm just curious, speaking towards unit tests versus system tests, you know, the unit tests are quick and fast to run, system long. Do you have any good patterns for how to organize that in terms of when to run each and how you kind of split them up smartly and, you know, how you identify system tests versus unit tests?
Yeah. There are a lot of ways to do that. I mean, you can really sort of split them up in your test file hierarchy, so that makes it really easy to say, run the test in this directory, run the test in this directory, to split them up. If you're using, I tend to like to keep tests for a feature or an area of the code together, so I don't tend to split them up that way. But PyTest gives you some tools that I didn't show for marking tests with a label, and then you can very easily tell PyTest, run the tests only with this label, or only without this label. And so I tend to use that for marking slow integration tests with a label that allows me to easily exclude them.
Okay, that's sweet.
When I'm running tests.
Thank you, Carl.
I'm starting to get into Python development from a Ruby background, and one of the tools that we have in Ruby for testing is AutoTest, where you can just leave a terminal window open and the test will run every time a file is saved. Is there something similar in Python?
You know, that's something that I've never done, not for particularly good reasons, just because, I don't know, I just switch back and forth and it's not that slow. But I've seen people demo tools like that, so I know that there are some. I'm sure if you come to the testing in Python Birds of a Feather session, there will be probably 5 people there who have tools like that they could show you, but I don't have one to recommend personally.
Thank you.
Rerun is apparently the name of one.
You mentioned during one of the workflows for adding features that there are some tools out there for writing tests in English and kind of testing those, but I didn't see any recommendations on any of those yet. Yeah,
you're right. That was an omission. So there's a very popular tool in the Ruby world called Cucumber that does that, where when you're writing those high-level integration tests, there's often a fair amount of setup you need to do, and the steps are not always simple. So what it allows you to do is you define a step name in English and then define what that actually does in code, and then you can write your test using those English phrases. There's a port of that to Python called Lettuce, which you could look into for that.
Hi. Python provides doc tests. That it means we can write tests in the doc string. I would like to know if this is a good idea. It looks like we can make the test very easy to be found, but it also makes your document very ugly. So it is good or not?
Yeah, I don't recommend doc test as a way of testing your code. It's tempting because, as you say, it looks like, well, I can put the test right here with the code and it kind of serves as documentation. But in practice, if you really try to test your code that way, it becomes very bad documentation because you're testing a lot of edge cases and it gets ugly. And there's also other problems with doc tests. They're fragile because they rely on matching output strings exactly. They don't have isolation, so if you have a bunch of tests in a row, one failure cascades and causes a bunch of cascading failures, so they aren't properly isolated. So I think doc test is a great tool for testing your documentation. Probably your actual documentation using Sphinx or whatever probably has code samples in it, and you can use doc test as a tool to run the code samples in your documentation, which I've actually done for these slides. But I wouldn't recommend, so it's a way of testing code samples and documentation. It's not a way of testing your code, in my opinion.
We are actually out of question time. Please give Carl a hand for his work.
Repository names that two different users are watching, and it'll give us a similarity score between those users. The similarity score that we use is the Jakarta index, which is the intersection of the sets divided by the union. Because this is software development, we're going to start out with an implementation that is slow and buggy. So that's what we have here. We iterate over the two iterables nested to build up a count of the intersection between them, and then we calculate the union and return the one divided by the other. So we want to make sure it works. We fire up the Python shell, and we try it out. We feed it some sample data, which we manually calculate what the correct answer should be. In the first case, the intersection between those two is B, and the union is ABCD, so that's 1 over 4. It should be 0.25, and in fact, that's the answer we get. We try another couple tests, and it seems to work correctly. But there is a bug.
Good morning, everyone. We are going to hear from Carl Meyer about getting started with testing. Carl is a core committer on Django. He works with virtual env and pip, so please give him a warm welcome.
Thank you. So a little bit about the plan for the next 25 minutes. I'm going to start off talking a bit about why you might want to write tests, how you might write tests, how to run your tests, what kind of tests to write, and a little bit about how to integrate testing into your development workflow. Quick story about me and Python and testing. I've been writing Python since 2002, professionally since 2007, writing a lot of tests since 2009. I enjoy writing tests so much that this slide deck has tests to test the code. Our buggy implementation doesn't know how to handle duplicates correctly. So in this case, the union ought to be AB, but instead it's calculated as AAB, so we get the wrong value. Fortunately, Python has a very nice built-in set implementation, so we can make our buggy implementation less buggy by using that. And that also has the side effect of taking care of duplicates correctly. And in fact, that does fix our bug. Now, even if we pass in lists with duplicates, we get the answer out that we expect, 1/2. But we rewrote every line in the function, so we better fire up the shell again and run all of our previous tests again to make sure we didn't break anything. And in fact, we go through and verify each one manually, and they all still have the same answer, so congratulations. We didn't break anything with our change to the function. Now this gets old, and it gets worse the more complex or the bigger the system gets. I was asking on Twitter about why people test, and I heard one story from Kumar McMillan about how he used to work on a 14-page survey app with manual testing, and anytime he would make a change to the 14th page of the survey, in order to see that change, he would have to click through and fill out 13 other pages of the survey, and then load the 14th page, and then verify his change. So this is repetitive and boring, and we know what happens with repetitive and boring tasks. We skip them because we don't like to be bored, and then we ship broken code because we haven't tested it. Also, this kind of manual testing is not easily reproducible. If you're running manual tests in your shell or in your browser or whatever, and you find a bug, you have to then copy-paste your shell session or try to describe what you did in the browser in English prose and send that off to your other developers in the project and try to put samples in it. I mostly do web development in Python. This talk is intended to be general beyond just web development, but that's my background. In terms of open source software, I've done some work on pip and virtualenv and on Django. So if you use those projects, you may have used some of my code. Let's make something. The plan for today is to make a GitHub recommendation engine. It's something that will go out to GitHub and look at the repos that you're watching, find people who are watching similar repos to you, and inform you about repos that people similar to you are watching that you may also be interested in. It's actually been done already, but that's not a problem. Here's the function we'll start with. It's a similarity function. It gives us a similarity score between two GitHub users. We pass in two iterables of repository